Hope everyone's doing well today. I'm going to cover 3.2. So this section's over correlation, so we're kind of going to start talking about graphs again, looking at some trends that are in the graphs, just to see, if we wanted to predict something that's going to happen later on the graph, well, maybe we can use the data that's already on the graph to, kind of lead us in the right direction. So the first thing I want to look at is this graph right here. So it's many in developing nations struggle to afford food. So it looks like we're comparing the percentage of people that can't afford food in a certain country in the past year, and we're comparing that to their GDP. And their GDP is basically just how much the average person makes. If you want specifically the definition, GDP stands for gross domestic product. And if you're really interested in that, I would recommend taking an economics class. I'm definitely not an economics professor, so I can't say that I'm any sort of expert on that. Okay. My first question, just to start off, I don't think this is in the book, but I just wanted to know what type of graph is shown below. Well, we don't see any kind of lines or anything, right? So it's not a line graph. We don't see any bars, so it's definitely not a bar graph. It's definitely not a pie graph, right? So the only other graph that we've talked about is a scatter plot, and this is a scatter plot, right? It's just a bunch of dots that we have scattered all across, and basically we don't have any kind of trend yet, kind of like a line graph would show, but we can kind of see that there are ones that appear, right? So if I look at the three different kinds, we're looking at advanced countries, that's the squares, so that's kind of like the US, Australia, South Korea, Greece, so those are the really developed countries. Emerging markets in the middle, I think they have Indonesia and China, and some other ones, Mexico, I guess. And then we have developing economies, so like Uganda, Kenya, Indonesia, and so on. And you can kind of see a pattern with these, right? So all these developing countries, it looks like a lot of their people can't afford food in the past year. And you can also see that they have a low GDP, right? So we see almost all of them are, to the left of where my pencil is showing. So if I was going to draw a line that kind of predicts where these are going to be, maybe I'll start, I don't know, just a guess right here, and it kind of goes down like that, right? So the higher their GDP is, it looks like the more people that can afford food, right? And then I can do the same thing with the other ones. If I look at the emerging markets, I see they're kind of all clustered around here. So I'm just going to try to guess and draw a line of maybe where that would be, something like that. And then finally we have the advanced countries. So maybe something like, I don't know, right there maybe, somewhere around there. And we don't necessarily have to start at 0, right, at this line right here for 0 GDP. We can start really anywhere we want. So I just kind of see that trend line there. Okay? All right, so this one says, write a sentence to summarize the trend shown on the graph. Well, we can all see that every one of these lines, some are steeper than others, but every one of these lines, they're kind of pointing down and towards the right, right? So it looks like the higher their GDP, the lower percentage of people can't afford food, right? So if we look at like Uganda, their GDP is really low, so a lot of people can't afford food, but as we go to like South Korea and Australia, they have a higher GDP, so more people can afford food in their country, right? So I'm just going to write that sentence down here. So I'd say the higher GDP, I guess the higher the GDP, the lower percent can afford food. Or can't afford food, sorry. Or can, yeah, sorry about that, can't afford food. So the higher the GDP, the lower percentage of people that can't afford food. Yeah, that's right. Okay. All right. And then B says, does the U.S. follow the trend shown on the graph? So if we look at the U.S., they're all the way up here, right? They're probably about maybe 25% can't afford food. I'm just guessing there, 25%. Do they follow the trend shown on the graph, or are they the exception? Well, if I look at specifically the U.S. as an advanced country, it looks like the higher the GDP for all of these, right, kind of point down like that. So if I was the U.S. with almost 50,000 for my GDP, I would expect the U.S. to be right about there, right? Just kind of the general trend line. So I would say that they definitely are an exception, right? And we kind of talked about this earlier. I think it came up on the midterm as well. I would call the U.S. an outlier because it's not really fitting the trend of the advanced countries of our graph. Okay, so I would say the U.S. is an exception, and the reason would be either they're an outlier, or you could also say that they are much higher than expected as far as how many people can't afford food in the U.S. So I'm just going to write food in parentheses just to make sure that's covered. Okay. All right. C says estimate the percent of citizens who cannot afford food in the past year in a country with a GDP of 48,000. So if I looked at 48,000, that would be maybe somewhere right here if I had to guess. That's almost where the U.S. is at as well, right? They're kind of close. But if I follow this trend line, I would expect them to definitely be like below this mark, but definitely above 0%, right? So I guess maybe 5 to 10%. So I'm looking at something maybe right around here-ish, if I was going to keep going on that trend line. So I would estimate between 5 and 10% of citizens who can't afford food in a country with a GDP of 48,000. So about 5 to 10% of the citizens. All right. All right. So we're going to talk about linear correlation, and the correlation is basically those lines that I drew on the last page. So when I have a scatter plot and it has a linear pattern, we say there's a linear correlation between the two variables. This means that the points generally fall close to a line. The points may be tightly clustered or even lie perfectly in a line. The points might also be more loosely arranged, and I'd say that's probably a good example of the last page. They were definitely a lot more loosely arranged. It says the best fit line can be drawn through the data points known as the trend line or best fit line. It does not necessarily pass through all or even any of the data points. So it says, for example, since the graph on the left has a trend line that's going up as you look from left to right, it says that has a positive correlation. So if we look at this, we kind of draw this trend line again, right? And we see that the general trend as our x's increase, so our x values increase, looks like our y values also increase. So I'm going to kind of write that in a way here. So we have ordered points. So if as our x's increase, so I'm going to represent that with a plus sign, my y's also increase, right? So as my x's increase, go this way, my y's also increase. They go up that way, right? So we have this positive trend line. Okay. And then the opposite of that, when we have a negative correlation, it's going to look like a graph like this. So as our x's increase, our y's are decreasing. They're going down, right? So I'm going to write that kind of like I did with an ordered pair here. So as our x's increase, so they go that way to the right, our y's are going to decrease. I'm going to put a minus there. All right. So a trend line always goes through the point of the mean of the x values and the mean of the y values. So if we just take the average of all these points, we add all these points together, and then we divide by how many there are, we're guaranteed to go through that point. Okay, and that's not super important. It's just kind of another fact that's kind of interesting about this. Okay, all right. So let's look at some examples. So it says for each pair of variables, determine if you expect a positive or negative correlation. So I'm going to draw a little bit of a graph for each one as well. So this one says the number of customers a company has and its total revenue for a company. So if I look at this little graph that I drew, I'm going to have customers on the x-axis here, and I'm going to have the total revenue on the y-axis. So as my number of customers increase, I would expect the revenue of the company, so the y-axis, to also increase, right? Because the more customers you have, the more revenue is going to have for that company. So I'm going to look at maybe something like this, right? So if we have zero customers, we're going to have zero revenue, and as we get more, it goes up, right? And this is just an example of our positive correlation, right? Because we have an increase. So this is a positive correlation. Okay, so it's a positive correlation. And sorry for the spelling if it's off there. Okay, so let's look at B. It says the number of hours of overtime worked and the number of hours spent with your family. Okay, so let's look at another graph here. So if I spend more hours of overtime here, what's going to happen to the number of hours spent with my family? Well, the more hours that I'm at work, the less time I can spend with my family, right? Because there's only so many hours in a day. So I'm going to say the more overtime, so I'm going to let y represent overtime and x represent the hours spent with family. So the more overtime I work, the less time I have to work with my family, right? So that's going to be maybe like a downward slope like that, right? So if I work a lot of overtime, I have no time to spend with my family. And if I work no overtime, I have a lot more time to spend with my family, right? So we have a downward curve or a downward pointing arrow. So that's just a negative correlation, right? So this is a negative correlation. Okay. All right. What about the cost of a car and the number of people willing to pay for it? Well, the lower the cost of the car means that more people would buy it, right? Like if it was a free car, there would be, almost everybody would want just a free car, right? Assuming it worked. And then the higher the cost of the car, the less people would be willing to buy it, right? Like I probably wouldn't be willing, or I definitely would not be willing to buy like, a $100,000 car. So I'm one of the people that wouldn't be willing to pay for that. So if I look at this this y-axis as the cost of the car, as the cost of the car increases, so if we start at like $100,000, there would be, very, very few people willing to pay for it. And as I go down to 0, so if this cost of the car is 0, almost everybody would be willing to pay for it, right? Because it doesn't cost anything. Okay, so that's another example of a negative correlation. Okay, what about D? D says the number of hours a student spends at an ACT prep course and her ACT score. Well, draw another graph here. The more hours she spends in an ACT prep course, the higher her score is going to be, right? Well, up to a point at least. So I'm going to say if she spends no hours in an ACT prep course, well, that's probably going to be her lowest ACT score, right? So I'm going to maybe put it like right there. So this is her ACT score, is this axis, and how many hours she spends at the prep course is the x-axis. So maybe she'll get a base score of like 20, I guess, on her ACT. And the more hours she spends at this prep course, the higher it's going to go, right? So maybe it goes up something like that, up to, I don't know, like 36 or, whatever the maximum is. Okay. Well, what kind of graph is that? Well, it looks like we're going up, right? So as my x values increase, my y values increase. And that's a positive correlation. So D is a positive correlation. So when two variables are linearly correlated, the relationship can be described by the trend line. So the trend line is basically just what we've been kind of drawing or modeling each time. Okay, we can write a linear function. Remember, a linear function, it looks like a line, right? So like that. The highest degree also is just first. So like an x to the first power is a linear function, if that's the highest degree. And we can use that linear function to represent this trend line and use it to make predictions for the x values that follow within the scope of the x values of the original data. So what we're going to do now is we're going to kind of compare our trend line to actual values that we get. All right. So one example here that we could have, this one says, in theory, an adult's arm span and height should be the same, but in reality, that's not always the case, right? Everybody's different. So this one says, the following table lists the arm spans and heights for a set of adults. Make a scatter plot of the data to graph the height and arm span. So we just kind of, I did that for you just to kind of save time so we don't have to graph those. So if I just look at the first one, so we have an arm span of 64 and a height of 65. So if I wanted to look at that, this is 64 right here. So I'm just taking 64 for your arm span, 65 for your height. So it should be that point right there. That's just 0.1, right? And we could plot more if we wanted to, if this graph wasn't empty. Okay. So after we made this scatter plot, I give you this trend line down here. So it looks like this trend line, and I'm not going to worry about completely, accurately plotting it on the graph. But if I had to guess where the trend line would be, well, it's going to be right in the middle of all these points, right? So if I was to graph something, maybe it's going to go something like that, right? It kind of splits all the points in half. All right, so in this case, I want to know what y is and what x is. Well, if I just look at the graph, I know this is always the y-axis, right? So I know my height is always going to be y. Okay? So my height is y, or my y is height. And what's my x? Well, my x is just the arm span, right? And I guess I got a little ahead of myself, so draw the trend line on the graph, so we kind of did that up there already. Okay? Alright, so this one says, now predict the height of a person with an arm span of 67 inches. Okay? So if I look at this trend line is going to help me predict what that's going to be. Right? So what is y? Well, y is my height, and that's what we're trying to predict, right? So I'm going to leave y by itself. I'm going to leave y alone. So y equals, and then I know I have this 0.9, and I know that x is my arm span. Well, I know my arm span already, right? It's 67 inches. We're given that. So let's plug in 67 wherever I see an x. And then we're adding 7.3 to that. Okay? So how can I start solving this? Well, the first thing I can do is multiplication, right? Because I have to do multiplication before I do addition. That's PEMDAS. So let's do that. So what's 0.9 multiplied by 67? Well, that's 60. So y equals 60, so I'm combining these two, 0.3, and then after, I'm adding 7.3 to that. Well, if I add those two together, what do I get? Well, I should get 67.6, right? And that's in inches. So I'm saying that if I was going to predict someone's height with an arm span of 67 inches, I would guess that they should be 67.6 inches for their height. And that's kind of our example, right? It said in theory an adult's arm span and height should be the same. And they are really close to being the same, right? 67 inches is really close to 67.6 inches. Alright, let's move on to the next examples. So the next example I have, this one's actually going to look at a bar graph instead of a scatter plot. So this one says the double bar graph from the Bureau of Labor Statistics shows unemployment rate and the median weekly earnings based on the type of degree earned. So it says answer the following questions that investigate the relationship between two variables. So what are my two variables here? Well, it looks like I have my unemployment rate's one of my variables, right? And the median weekly earnings could be my other variable. Okay? All right. So A says, describe the general trend that you see on the graph. Are there any exceptions to this general trend? Give examples if possible. So what do I see on this one? Well, I see that my unemployment decreases the higher degree I have, right? So if I have less than a high school diploma, that's about 9% unemployment, and it goes down to about 2% for the top two, right? So if I was going to look at a trend, it's probably something like this, right? So it's a little bit misleading right here because we know that it's going down, but it kind of looks like it's a positive correlation, right? And we're kind of looking at this wrong. So if I wanted to, I could kind of switch it like this, right? So this is the x-axis, this is the y-axis, and now I can see it's clearly going down, right? And we can kind of tell that it's going down just from the numbers as well, going from 9, which is a bigger number than 2, right? It's going down, okay? All right, so we know that this is the general trend is that it's the unemployment decreases the higher degree you have. The higher degree you have. Okay. And then I'll get to the examples if possible for the exceptions. But let's look at the median weekly earnings. So if I was to look at this one, if I drew a line from the bottom to the top one, well, this also looks like a positive correlation, right? But I'm going to use the same trick here. So instead, I'm going to look at it like this. And what am I seeing here? Well, it looks like you're going from less than a high school diploma, and you're increasing as you go down, right? Or as you go to the left, right? So we're kind of increasing values as we keep going on. So I could say that the higher degree you have, the higher your potential earnings, right? So it's almost the same as the first graph. So the first graph says as your unemployment decreases, the higher degree you have. Well, the higher degree you have, the more earning potential you have, right? So the higher degree the higher your earning potential is. The higher your earning potential. Okay? And then what exceptions do you see? Well, the only time I see the graph change as far as its trend is with the doctoral degree, right? So we keep going down, down, down for until the professional degree, and then we kind of go up for the doctoral degree, right? And in the same respect, we go up, 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 and then we finally go down for the doctoral degree. So I would say the exception in both cases is the doctoral degree. So that's our exception here. Okay. All right. Let's look at B. It says, notice under the last bar on each side of the graph is an average. These numbers are not simple means of the values listed in each category. So what that basically means is we see this line right here, right? And this is kind of our average. So an average, a way that you can say an average in math is a mean. But we know that this isn't a simple mean, right? So we're given that. So what kind of mean could it be? Well, the only other mean that we've talked about is weighted means, right? And if we think about weighted means, we have our weights and our values. Well, I know that my values are all kind of even, right? Like this one's 9, this one's 6, this is 6, and so on. So these values aren't going to change, but what's going to change is the weights. And the weights in this case are just how many are in each category, right? There's a lot more people with a high school diploma than there are people with a professional or a doctoral degree, right? So our average here, the 5% of all workers, is definitely going to be weighted more towards these three categories because there's so many more people in those three categories than there are in these top 5, right? And the same thing on the other side because we're still comparing degrees, right? There's so many more people in these bottom 3 than there are in these top 5. So it's definitely weighted more towards these bottom 3. Okay? So how are they calculated? Well, we just used a weighted mean. Okay? So we just used a weighted mean. And if you wanted to check just to make sure that the simple mean is not correct, well, if you wanted to do that, you would just weight all these evenly or the same. So you would just add all these together and divide by how many there are. And you'll find out that it's not 5% here, and it's not 839 there. Okay? All right, and then C says, to analyze the data's relationship further, let's convert the earnings from weekly to hourly earnings, assuming that they worked 40 hours of work per week. And then it says, record the unemployment rates and the hour earnings in the following table. So let's do that. So if I do that, well, I know that my unemployment rate is going to stay the same, right? I haven't changed that at all. Sorry, just bring it up here. Okay. So my unemployment rate hasn't changed at all. So I'm just going to take the unemployment rates right here, and I'm just going to write those in my column here. Okay. So my unemployment rate for a doctoral degree is 2.1, and then it's already in percentage, right? My professional is 1.9%. My master's degree is 2.8%. My bachelor's is 3.5%. My associate's is 4.5%. Both my some college and high school diploma are 6%. And then finally my less than a high school is 9%. Okay? Alright, so we have that, but then we have to find out the hourly earnings. Well, we're given weekly earnings up here, right? So how can we find a weekly earnings, change weekly earnings into hourly earnings? Well, we know that we're assuming that they work 40 hours a week, right? So if this is their weekly wages, why don't we just divide everything here by 40, and then we'll find out how much they earn per hour, okay? So I'm just going to show that on the doctoral degree, and then I'll write in the answers here for you, okay? So let's do the doctoral degree. So we have 1,591, divide that by 40 hours a week. So that's how much they make a week, divided by 40 hours a week. So we would say that the doctoral degree people earn about $39.78. Okay? So those two numbers, and we round off to the nearest cent. So they'll make about $39.78 an hour. Okay? Well, I can do the same thing for the professional degree, right? So instead of this 1,591, we're going to divide it by 1,639. Okay? So if I do that, they should make 98, and then I can keep doing that, right? Divide the next one, the master's degree, 1,326. Divide that by 40 hours. We should get 3315. the bachelor's degree should get $27.53. The associate's degree, let me rewrite that, sorry, that was bad. The associate's degree should make about $19.80 an hour. The some college no degree should be making about $18.53 an hour. The high school diploma makes $16.70 an hour. And then lastly, the less than a high school makes $12.20 an hour. Okay? Alright, so if we have all those down now, let's think about this a little bit. So, if I have my unemployment rate, so it looks like my unemployment rate's high, right, and it goes lower as I go there, and then my hourly earnings increase, right, from $12 all the way up to about $40. Well, that almost matches, or that exactly matches the graph up here, right? My unemployment rate's decreasing, and my hourly earnings instead of my median earnings are still increasing, and then I still have this exception where it kind of drops off a little bit for the doctoral degree, right? Because all I'm doing is dividing everything by 40, so they should all still fit this same trend, right? They keep increasing and then they just decrease on the last one, right? And that's exactly what we see. All right, so let's look at the next page. So I couldn't fit everything on this problem on the last page, so I posted the answers here just in case you wanted to check your own. So D says, let's make a scatter plot for the median hourly earnings versus the unemployment rates. That is a graph the unemployment rates on the x-axis and the hourly earnings on the y-axis. So it says this choice is arbitrary since we could pick either variable to be x and y. Right, so I just graphed it for you just to save some more time on the video, and then also just to keep this constant. So the x value is always the unemployment rate for everyone, and the hourly earnings is always the y. Well, if we graph this, it looks like, what do we see? Well, this person right up here, so this highest earning, is definitely going to be the professional degree, right? It's almost $41. Yeah. And their unemployment rate is just under 2%. And that's what we see, right? We look at our 2% unemployment rate, it's just to the left of that, right? So they've already graphed all these for us, and we see this trend line, right? So if I was looking at that trend line, what is it, I guess letter E, what does your scatter plot suggest about the relationship between the earnings and the unemployment rates, and what kind of correlation is suggested? Well, it looks like the higher your unemployment rate, so the more unemployment rate you have, the less hourly earnings you're also expected to have, right? And that makes sense. Like there's not very many doctors, right, compared to everybody else. So they make a lot more money because we need them, but there's not as many people that can fill that role. And that's also why their unemployment is lower, right? Because there's more positions open and there's less people applying for those jobs. Okay? So it looks like the relationship is the higher your unemployment. So I'm going to say the higher percent of unemployment. Unemployment. Equals a lower hourly earnings. So I'm just going to put a $sign. So the lower amount of money that you make. Okay. And then it says, what kind of correlation is suggested? Well, it looks like as our x values increase, our y values decrease. So that would just be a negative correlation, right? Because it's going down. So that's a negative correlation. Negative correlation. Okay. All right. So F labeled the trend line on the scatter plot. So I already did that for you. We already drew it. Okay. And then H says this is the actual trend line. So this is the equation, and we'll talk about this in a later section. But this is the equation that we'll need to draw exactly what this trend line is. Okay. So for now, we're just going to take it as a given, but we will draw it in a later class. So it says H equals negative 4.2 U plus 44.9. So U is just the unemployment rate, so that's just our X values. And our Y value, or H, is just representing the hourly earnings. So it's basically what we just wrote up here. The higher percent of unemployment equals the lower money. But they quantified that. So they actually have numbers for this now, right? So what if we're given something? So what if we're given, it says predict the hourly earnings for a job that has an unemployment rate of 5%. So we're given that U equals 5. Our unemployment rate is 5%. So let's plug in 5 to this formula. So we're going to plug in 5 where we see U, and we can find out what H equals. So what our hourly earnings equals. Okay. So I am going to omit that here, and I'm going to let you solve that. Okay. So I want you to just try that as an exercise. I'm going to let you solve for H here. Okay. All right. All right. Let's look at the next one. So the next one, we're going to talk about residuals a little bit. So it says residuals is just the difference between the actual and observed values and the corresponding values predicted by the equation of the trend line. So I'm going to go back to the last page really quick just to show you what it means by residual. So residual is just your observed value subtracted from your predicted value. So if I look at this example down here, if I look at this dot right here, this is my observed value. And my predicted value, we just make a line straight down, would be this right here. That's my predicted value. And all I want to do for my residual is I'm subtracting the observed value from the predicted value. So basically I'm just finding the distance between this point right here and this point right here. So I'm just looking at that right there. Okay? So if I see that my observed value is higher than my predicted value, if I do that minus that, I'm going to end up with a positive number, right? Because this is a bigger number than this. So if my observed value is greater than my predicted value, I'm going to have a positive residual. And then likewise, if I have a number like this one, where the observed value is lower than your predicted value, I'm going to have a negative residual. Okay? All right. So now that I've kind of talked about what residuals are, we'll do an actual example here. Okay. So this one says, a professor is wondering if a final exam really provides additional information about what his students have learned during the semester. To help him decide, he looks at the students' grades from the previous semester, both before the final exam and on the final exam. So if we look at it, it looks like we have the students, a bunch of students' overall grades before the final exam, what their actual final exam grade is, and then we want to find what their predicted final exam score is. Well, I see the word predicted, right? So I know that residuals might be involved later because we have a predicted value. And the way that we can predict these is just using the trend line. So I actually gave you a trend line down here. I'm telling you this is what it should be. Okay? So our final exam grade, and I should say this is the predicted final exam grade. So predicted final exam grade is equal to 1.0138 multiplied by our overall grade before the final exam, so this column. So we're multiplying that by this column, so for each one. And then we're going to subtract 4.1629 off that. So that's what we can find for our residual here. Okay. So if I do that, let's fill in the columns here. So let's do that. So how can I find my overall grade for this very first student in their predicted final exam score? Well, I just plugged a 72 in to their overall grade before the exam score, right? So let's do that. So I'm going to have 1.0138 multiplied by 72, and then we're going to subtract 4.1629. Okay. So if I do that, if I subtract those two amounts, what will I get? Well, let's try that on the calculator. I'm going to grab my calculator here. And I'm going to do 1.0138, multiply that by 72, and then I'm going to subtract off 4.1629. So if I do that, and I notice that that's not showing up very well on there. So if I do that, my predicted exam score, after I solve this, is equal to 68.8307. So I'm just going to round it to 68.83, or 68.8 is fine. Okay, and now we can do that for the rest of them, right? So I'll set up the next one for you, and then I'll just give you the answers to the rest of them, so you can try them out if you'd like. So the next one, I do the same thing. I'm going to have the same formula, but instead of having 72, I'm going to plug in 68. Okay, so let's do that. So we have 1.0138 multiplied by 68, and then subtract off 4.1629. Okay, so if I do that in my calculator, I get 1.0138 multiplied by 68, and then subtract off 4.1629. Okay, so it looks like after I round, I should get 64.8. 64.8. Okay. Now, how can I find the residual? Well, just remember the definition of the residual up here, right? It's just the observed value minus our predicted value. So how can I find that? Well, all I needed to do is, what's my observed value here? Well, my observed value is their actual final exam grade, right? So that's where this column comes into play. So this is my actual exam grade, and this is what my predicted exam grade is. So I'm going to say this is my observed values, and this is my predicted values. So all I'm doing is subtracting them, right? I'm subtracting my observed value from my predicted value. So I do 73 minus 68.8, and I get 4.2. And on the next one I have 54, and I'm subtracting 64.8, so I should get a negative 10.8. Right, and I can go down on the list. So I'm going to fill in this chart for you, and I'll let you check it if you'd like. So the next one, the third student down, they should get a 78.0. The fourth student down gets an 85.1. The next student 74.9. Then 76.9. Then we have 89.1. Then we have 66.8. 62.7. 71.9, and then to find the residual, we just subtract this column from this column, right? So this should be a negative 2.0 for the next one. Then we get 0.9, then we get 0.1, 4.1, 0.9, a negative 14.8, a 19.3, and then finally a negative 1.9. Okay, so if we look at this, if we have a positive residual, so like this very first example, if we have a positive residual, what does that mean? Well, that just means that they got a better observed score than what was predicted, right? So they just got a better final exam score than what was predicted. So another way to say that is the student did better than expected. So a positive residual, the student did better than expected. Than expected. And then I did a little typo here, so this should be a negative rather than positive on part D. So what does a negative residual tell you about a student's performance on a final exam? So like the second person. Well, it looks like they did worse on their exam than what was predicted. Right, so another way to say that is they did worse than they expected. So the student did worse than expected. Worse than expected. Okay. And then finally it says, how well do you think the model given by the equation of the trend line predicts the final exam score? And then should the professor still need to give a final exam? Why or why not? Well, if I look at these residuals over here, so this is just the difference, right? So if I have this trend line, and maybe it's something kind of like this, maybe, if I was to guess. It looks like we have some people that are like maybe 4 points above, some people that are like 10 below, you know, like there's quite a bit of difference between 10 and then the expected residual. So I would say just because all these exam scores, they're almost like outliers, right? Like these two here, the ones over 10 with an absolute value of 10. I would say that this final exam definitely is necessary, right? Because there's a lot of people that are scoring like way above or way below the exam score, so maybe they still have a little bit to learn. And as a good guide, there should always be a final exam, right? I'm sure it's probably required by a lot of universities to keep up the rigor in classes and stuff. So, does the professor still need to give a final exam? Usually, your answer is always yes, right? So, yes, he does need to give the final exam. And the reason I would give the final exam, this needs to be given, needs to be given, and the reason it needs to be given is because some of the scores, some of the exam scores that were given are way higher or way lower than the existing or the predicted exam score, right? So some exams are way higher or lower than predicted. Right, and that makes sense. So if everybody did exactly how the exam score is predicted, their score in that class, or their percentage, you know, if they get an A, B, C, or whatever, isn't really going to change if they get exactly these, right? But some students, like maybe this last student, they got an 82, but before they had a 66, that probably brought them up to like a C, so they actually passed that class versus failing. So if they didn't have that final exam, the student would be stuck with a 66 and they would get a D, right? So that the final exam definitely helped that student out specifically. Okay. All right, so that's the last lecture for this week, and I'll plan on uploading the next ones in, I believe, 2 weeks, because spring break is next week.